All right, and so we are now ready for our third example. And once again, I'm still using that exact same data, letting capital X being the random variable representing the age of a student at HD college. So once again, the intention here is that X represent a population data. And so this table right here is the given, so think about some super powerful computer at that HD college already provided us the probability distribution. So probability distribution is now a more convenient way of viewing large data, very large data, instead of seeing the entire list. So once again, let me clarify a different understanding that I've had people questioning me. So now if I'm talking about there's a computer that's able to store data this large, and why not giving us the complete list? But think about if that really happened, where the computer does give you a large list like that, and how many people would like to see that list? And so when data become once again that big, where we ignore the n count, it really means it's too big, even though there is a list available. We just simply we should be better off by reading a probability distribution like this, so that we have a more general idea of the data rather than just looking through the entire list one by one and count and knowing how many 17s, how many 19s, and so on and so on. And that's the whole point of using, again, that's the whole point of using random variable, and it's a very convenient way of representing the population data. But so now into this example, then first question I'm going to bring up, question A. Let's find the mean value of the random variable X. And so as soon as I finish writing down the question right here, have that clear understanding that the intention of this problem, calculating the mean value, is to aim at a population data. That means what we're looking for here is intended to be the population mean. Simply because the data here we already ignore and we never ask for what that n count is. So if you are going with this route right here, and I have seen people doing that in my classes, and I've seen people doing that commonly out there as a mistake right here, but 17 plus 19 plus 21 plus 23, and hey, there are 4 values being listed. Yes, this is a list, but it's not the list as a list of the data. It's just the list of all the distinct value, but then correspondingly it came with these came with the probability associated. So if we are only dividing by 4 here and claiming that this is our mean value, we're way off the hook right here. So this is the incorrect way of doing that. The correct way now is to produce, even though many textbooks and other instructors give out the formula with the summation notation, I still prefer to use the written out formula right here in this work, so that more people are able to follow the steps right there. So to find the population mean, we look at our first data here, that distinctive data value for the random variable X being 17, but now we are going to multiply with probability correspondingly being 0.2, and so we're done with the first pair. The next pair, now we're going to need to add to that first pair with the next pair being 19 as the value, multiply with probability 0.25. And the third pair here of value, we're looking at 21 as being the distinct value and probability being 0.45. And the last pair, and we're done. 23 on the left hand side is the value distinctively, and the right hand side is that probability correspondingly being 0.1. And so now just simply give a calculation here. So calculation shows mean age on this HD college right here, at that HD college is 19.9 years old right here. And now what we found here is once again the population mean value. The population mean because we calculated the mean value out of the entire population data, not only a small set of data. And now allow me to give some insight about the work that we have done earlier in terms of calculating the population mean. So once again, with our random variable x right here being understood as a random variable to represent a population data, the random variable had the following probability distribution. So observing the work that I was doing in terms of calculating the population mean here, then notice that in the first term of my sum right here, it was 17 here being the first value. And the whole idea once again is a probability distribution lists out the distinct values that we can recognize in our population data, and these are the corresponding probabilities. So 17 here came from the first value in our data, and we can namely call that, so this is x1, the first data value that was listed in the probability distribution. And so what happened here was that I multiplied the first distinct value with the probability that x equals, this 0.2 right here is the probability that x equals 17 specifically. And so similarly, 19 here was the value on the second value on my list, x2 right here. And the 0.25 here is understood as the probability where the random variable equals 19. And so on and so on. That's how it happens with each of these terms in our population mean calculation. When the answer came down to mu equals 19.9 right here, I hope viewers also have noticed that the mean value now has a new notation. The notation that I use here is a mu instead of x bar. So I will come back and explain more in details, but for now, as of this moment right here, we use a mu as a symbol for population mean. Now, before I'm moving on to the next question in the same example here, I need to make another note. So, in a different video a little while ago, then I posted an instruction of how to use the stats button with a TI 83 or 84 calculator. Now, I have to really clarify in case anybody is falling into that mistake right there. But calculating population mean from a given probability distribution like this, there are no technology that can help you with that. So this route using the stats button on the TI 83 or 84 calculator will not work on this. The reason is simple. The stats button in your TI 83 and 84 calculator can only find for you the mean value once you already have the complete list of data and given to the calculator. But here what we have is only we don't have the complete list. What we have is the probability distribution. So we did not, in other words, again, I have to remind everybody that this table is not writing out how many 17s there were in the data, how many 19 there were in the data. This data did not tell you that. It only tells you that 17 in the data is happening at probability 0.2. 19 as a value happens in this data X right here at probability 0.25. And so, as a matter of fact, not too many technologies out there outside of the TI 83, 84. There are not too many technologies can handle the calculating probability on a probability distribution like this. So make sure you know how to use the formula. And normally, when it comes down to a probability distribution, then usually our work for finding mean value is quite short, and we already skipped. We save ourselves from too many operations, so we only have simply just adding and multiplying, no more division. So it shouldn't take too long. And so only use your calculator to help you calculate, but it won't have any direct function or feature to handle this population calculation. And so now let's summarize our understanding as far as how we came up, as far as what we came up with as a new formula for calculating population mean. So generally speaking, anytime we let x be a random variable or an RV right here, and of course x being a random variable is to represent a population data. And so in a probability distribution of x right here, left hand side column, we're listing out the distinctive values, the distinct values of your random variable. So your random variable is maybe recognized to have values distinctively x1, x2, x3, so on, up to the last distinct data value in your population could be xk, the kth x value. And then, as we already have seen throughout our understanding so far, then the right hand side column here is to indicate different probabilities corresponding to when your random variable x equals x1, when your random variable x equals x2. So here's I'm filling it out. So probability when capital X equals x1, that's what we put in on the right hand side column corresponding to that same entry. And here probability when capital X equals x2, and that is the same corresponding entry when x being x2 right here, and so on and so on. So this is generally a probability distribution. And of course, provided that we add up all the probabilities here and already ensure that all these probability values add up to 1. And then at our last entry here, probability when x equals the kth x value is there. And so now, if we look back into our work previously, in just now happened, then the mean value seems like the new method we came up here is population mean is found by we look through our table here. We're looking at our probability distribution, and first value distinctively is being x1. I am going to multiply the value with the corresponding probability when your random variable equals x1 as a product. And I'm moving on to the next one, namely x2, and I need to multiply that value on the left hand side with the probability value on the right hand side equals x2. And I'm going to keep advancing. I'm going to keep adding until I reach to some of my ending one here, namely x k, or the kth x value multiplied with the probability when x equals x of k here. And so really I ran out of space here in my writing board, so I have to write it down here. But really, if you have more space in your own paper when you're taking notes right here, then it's really just one formula that keeps extending further out to the right hand side. And then this work we're doing here will end at the kth value distinctively on our list right there. And so the mean value here, once we come up with the final value, we are going to use a symbol mu right here. So what happened here? X bar used to be used as mean, but now we switch from using X bar to this new symbol over here, because remember, what I stated earlier is what we're looking for here is the kind of mean value for a population. And so, and I will come back to explain the difference between X bar and mu over here. But for now, anytime we are calculating population mean, we must be using the mu symbol. So mu here is the population, or the symbol for population mean value. And there are tons of website resources showing you how to draw the mu symbol. This is just my style of writing it, but you can look it up on Google and it will show you how to write a mu symbol. But pronunciation, so this is say mu. So what exactly is a mu symbol? The mu symbol is simply a lowercase Greek letter m, so it stands for mean right there. So lowercase Greek letter m, but and we use that lowercase symbol, that lowercase Greek letter m right there. Now we call that new right there, is to represent the way how we find population mean. So we made it to a new formula. So calculating the mean value, same fundamental, started out, added up all the values and divide by how many there are, but now surprisingly we derived a new formula. We recognized a new formula, and this new formula here, throughout our example, you're gonna find out that it is particularly good in the case where instead of having the full complete list of data, you're only given as a probability distribution. And so this formula of how you can find the population mean is a good place for calculating the mean value when you are in a probability distribution like that. All right, and so now we are ready for part B of this same example. Example 3, now we're looking at part B. So we would like to find the standard deviation. This data X right here. So this is one gigantic data, which is simply represented by a random variable X. So now with this standard deviation here, once again, I need to remind that it's intended to be the standard deviation of the entire population. So it's called the population standard deviation. And then symbolically, we are using the sigma symbol for this population standard deviation. Okay, and so as far as the work, once again, and I have to warn all viewers ahead of time, but once again, we won't have any fast technological tools to help us with this, because what we have here is not a complete list of data. We only have here a probability distribution of the data. So we must use the formula. So 17 square times the probability 0.2. That's the first step. And then we're going to add the next one here is a pairwise product of 19 square times 0.25. The next one, 21 square times 0.45. The last one in our sum is 23 square times 0.1. But now, and you can see that I'm writing down here in particularly a certain order so that it keeps your work safe. So after we finish adding all the pairwise products, then we're going to subtract. And keep in mind, we already found the mean value from part A, and so mean value was 19.9. So now we're going to subtract the square of 19.9. And then after subtraction, we are going to take an overall square root. And that is how we're calculating our population standard deviation. So sigma equals with that square root quantity. And so now I'm ready for the final answer. Calculation comes out to be 1.84. And that is how we're calculating our population standard deviation. All right, so now what's the generality of the work to calculate the population standard deviation after seeing part B of example 3? Allow me to point that out in this separate space. Looks like the first term came out inside of that square root. The first term of the summation really was just the value x1 in the probability distribution being square. So the value x1 being square, and we multiply with the corresponding probability when x equals x1. And x here I mean the capital X, the random variable. Then we advance over to the next entry, simply square the value x2 square. Square that value x2 and multiply that square of x2 with the probability value when x equals when capital X equals x2. And we add these two, and we'll keep doing this. We'll continue doing this. For x3 square, multiply with probability when capital X equals x3, and we'll continue doing this. And like I said again, I inconveniently, my board space is short, so I can't write any further out to the right hand side, but think about when we're actually doing the work, we just continue further to the right hand side until we hit to the end of our list of our distribution, our probability distribution. So here it's xk, the kth value being square, multiplied with the probability when the random variable x equals xk. And once we are done adding up, we are going to subtract one time the square of the mean value. And after the subtraction, we are going to take an overall square root inside of that. And that is a new formula we recognize for calculating population standard deviation. And so in a cleaner space here, let me just simply rewrite that formula for the population standard deviation. But what's going on there? That generally from any probability distribution, all you need to do to calculate the population standard deviation is that we go x1 square multiply with probability when random variable capital X equals x1, and we move on. Repeat x2 square times probability when capital X equals x2 plus, then we move on to the third distinctive data value x3, square the value, multiply with the probability correspondingly for x3, and then we keep doing that until we reach the last one in our data, being xk square multiplied with probability when random variable x equals xk. After we're done adding, then we are going to subtract one time the square of the mean value, and then we're going to take a final square root. And I purposely write down my formula this way so that you can see there's a certain order of operation. And the closer you stay with the order of operation, it's going to get us a successful answer. And so now this new formula is the formula to calculate population standard deviation. And so population standard deviation use a symbol sigma to indicate a population standard deviation. So anytime we are calculating population standard deviation, let's use a sigma for population standard deviation. So we used to use a lowercase s, but lowercase s is not the right symbol now for population standard deviation. So anytime we're calculating population standard deviation, make sure you use this symbol over here. It's called sigma. And sigma is a Greek lowercase letter s. So it's still s, but it's not the English version. So English version we save that for the smaller kind of data, the kind of data where we know the n count. And here when we're calculating population standard deviation, then we are going to use the sigma symbol. And so consequently, this formula right here we are just derived right here is a formula that calculating our sigma value. And at this point, after studying carefully all about the population data, then we're going to start asking ourselves, so what about those data with the n count? So let's say think of your data 1, it has an n count being 40. Think of some other data set that has an n count. But so now a rule of thumb is when your data has a known n count, because when it's a population and the n count is too big, that we have to ignore it. So when we're working with any problem that having an n count, then usually it's a small n count or some value that we can count through. And so if those data are being have an n count right here, then we regard to those as sample data. So data having an n count is now regarded as sample data versus population data. So we just now learned population data as we have to ignore, we must ignore n. But so now if we're looking back at any data we have been working prior to this point right here, then those data are regarded as sample data, where they have known n count. And so for now we're just beginning working with population data and making that clear differentiation between sample data and population data. One major difference is that sample data has a known n count. And the reason for this, because sample is usually, and that's the whole point, we can never pick a sample that being as large as the entire population. Usually much smaller than a population. And that's why when it's much smaller and later on when we formally learn about picking up sample data and picking or learning about doing sampling of the data right here, then we're going to learn the reason why sample has to be much smaller than the population data. But so for now, since our journey just about begin distinguishing between population data and sample data, and all we have to keep in mind is population data is the kind of data being so big that we ignore the n count, and in a sample data, then it's something that we actually collect, and so it's a lot of time much smaller than a population data. And so in that way it's a good place to have a known n count like that. After making a clear explanation the difference between population data and sample data, so we can categorize our understanding into a table like this. So of course numerical data we're working with, but so now it's being split into two different settings. So our data could be either a sample data or being a population data. So data can be a sample data, something small with the n count. So what we know is being a sample, just like what we've learned moments ago. That sample being a sample data, we have a known n count. And for population data, we have to ignore. We haven't ignored n. It's there, it's out there, but it's so big that we have to ignore it. So as far as the size of the data, we have a known n count for sample data. We have an ignore n count. We have an ignore population size, because it's impossible to get that. And then in either settings, either you are working with the sample data or you're working on the population data, we can always find a mean value. So mean value in the sample data is regarded as a sample mean. So sample mean here, beginning of the quarter. So now if you're looking back, then so all that time throughout the beginning of the quarter until now, we have been using this symbol for X bar. My intention is to start out teaching stats, always approach things as a sample data so that everybody has a nice clear understanding. And then now once everybody has a clear understanding, and then it's time to move on to the population data. But so, like I said again, sample data or mean data, we can always find a mean value. So mean value from a sample, or now regarded namely as a sample mean, we use the X bar, the lowercase x with a bar. That's the sample mean symbol formally for sample mean. And so we just now learned throughout this lecture that population mean, see, it's a population data, no matter how big, but we can find a mean value. So mean value of a population data regarded as a population mean, we use symbolically a mu symbol right here. And same way, once we found a mean being the center of the data, either in a sample or in a population, mean always for being the center of the data. And so once we pass center of the data, then standard deviation need to be calculated, average spreading of how data values being spread away from the center. And so now if your data is being a sample data, then we can find the standard deviation of a sample data. We namely refer to that as sample standard deviation. Symbol we use for that, that's the symbol we've been using throughout the quarter until now, lowercase letter s. But now when your standard deviation become a population standard deviation, or in other words, if you're calculating standard deviation of a population data, make sure you are indicating with the symbol sigma right here. So there's a sample standard deviation and population standard deviation.